On July 1st, 2025, at precisely 14 hours 37 minutes Universal Time, the universe delivered a question wrapped in ice and stone. The Atlas telescope system in Chile, designed to scan for potentially hazardous asteroids, captured something that would challenge every assumption we held about visitors from beyond our solar system. In that moment of discovery, frozen in digital pixels, lay an object that would force humanity to confront a possibility we had long imagined but never seriously faced. What if some things that look natural aren't? The initial detection seemed routine, a faint smudge of light moving against the stellar background, catalogued as C/2025N1. Within hours, however, the orbital calculations revealed something extraordinary. This wasn't just another comet tumbling through our cosmic neighborhood. The mathematics told a story of impossible origin, with an eccentricity of 1.47, far exceeding the value of 1 that marks the boundary between bound and unbound objects. This visitor was definitively interstellar. They designated it 3I Atlas, the third confirmed interstellar object to enter our solar system. But unlike its predecessors, this visitor carried signatures that would blur the line between natural phenomenon and something else entirely. The automated detection systems had done their job perfectly, flagging an anomaly in the vast emptiness. What they couldn't know was that they had potentially discovered either the strangest comet ever observed or evidence that we are not alone in the universe. The speed alone should have been our first warning. At 130,000 miles per hour, 3I Atlas was moving faster than any natural object we'd previously tracked through our solar system. To put this velocity in perspective, it could cross the entire United States in less than 90 seconds. This wasn't the leisurely drift of a typical comet, bound by our sun's gravity. This was something racing through our neighborhood with the momentum of another star system entirely. Initial spectroscopic observations revealed a compact coma surrounding the nucleus, suggesting active outgassing as solar radiation warmed ancient ices. This seemed reassuring, familiar even. Comets were supposed to develop comas as they approached the sun. But the chemical signatures hidden within that glowing cloud would soon tell a very different story, one that would challenge our understanding of what interstellar visitors should look like. The trajectory analysis revealed another layer of peculiarity. 3. I Atlas wasn't just passing through randomly. Its path would bring it to perihelion, its closest approach to the sun, on October 29, 2025, threading perfectly between the orbits of Earth and Mars. The precision of this trajectory, while not impossible by chance, raised questions that would only multiply as more data arrived. The object would pass within 1.88 astronomical units of Earth, roughly 280 million kilometers. Far enough to pose no danger, but close enough for detailed observation. NASA immediately mobilized its most powerful instruments. The Hubble Space Telescope adjusted its schedule. The James Webb Space Telescope prepared its infrared sensors. Ground-based observatories worldwide turned their mirrors toward this cosmic interloper. This coordinated response represented more than scientific curiosity. It reflected an understanding that had been growing since Oumuamua's mysterious passage in 2017. Not everything that enters our solar system from interstellar space behaves according to our expectations. As July progressed into August, the accumulating data painted a picture of an object that seemed to follow the rules of physics while simultaneously breaking them. It was active like a comet, but wrong in ways that were difficult to articulate. The brightness was off. The chemistry was unprecedented. The behavior patterns didn't match our carefully constructed models. We had discovered something that was either a natural phenomenon operating under conditions we'd never encountered, or something that was pretending to be natural while being anything but. The mathematics of 3E Atlas's approach told a story that began long before human civilization existed. This cosmic bullet had been traveling through interstellar space for millions, perhaps billions of years, maintaining its incredible velocity through the vast emptiness between stars. At 130,000 miles per hour, it carried more kinetic energy per kilogram than anything astronomers had previously tracked through our solar system. The hyperbolic trajectory was unmistakable. While elliptical orbits eventually return, like Earth's annual journey around the Sun, hyperbolic paths open into infinity. They are the signatures of objects that don't belong here, gravitational tourists passing through without stopping. The calculations were precise and unforgiving. 3 Eatlas had what astronomers call a V-infinity of approximately 25 kilometers per second, its velocity relative to the Sun if it were infinitely far away. This measurement alone confirmed its interstellar origin beyond any doubt. But velocity tells only part of the story. The approach vector, the direction from which 3 Eatlas entered our solar system, pointed back toward the constellation Lynx. When astronomers traced this trajectory backward through time, accounting for the gravitational influences of nearby stars, they found something unsettling. The path suggested an origin in the galaxy's thick disk population, a collection of ancient stars that formed when the universe was perhaps half its current age. If these calculations were correct, 3 Eatlas had been wandering the galaxy since before our Sun ignited. It had witnessed stellar births and deaths, passed through regions of space we can only observe through telescopes, and somehow survived the harsh radiation and micrometeorite impacts that should have ground any small object to dust over such timescales. The fact that it remained intact and active suggested either incredible luck or unusual composition. The timing of its arrival in our solar system raised questions that transcended pure celestial mechanics. Statistical models suggested that interstellar objects should arrive randomly, their trajectories scattered across all possible directions and arrival times. Yet 3 Eatlas had appeared just as humanity's technological capability to detect and study such objects reached maturity. Was this cosmic coincidence or something more deliberate? The energy requirements to achieve such velocity through natural means were staggering. Gravitational interactions with giant planets could accelerate objects to high speeds, but usually in random directions. The precise trajectory of 3 Eatlas suggested either a remarkable series of gravitational encounters or an initial launch velocity that defied conventional planetary system dynamics. Some researchers began calculating alternative scenarios, including the possibility that this wasn't random debris, but something launched intentionally. Comparative analysis with previous interstellar visitors added layers to the mystery. Oumuamua had tumbled through our solar system at 26 kilometers per second, showing no visible outgassing despite mysterious accelerations. Borisov had arrived at 32 kilometers per second, behaving like a textbook comet with its prominent tail and familiar chemistry. Now 3 Eatlas was blazing through at nearly double Borisov's speed, showing activity, but with chemistry that made no sense. The detection itself had been remarkably fortunate. The Atlas system, designed to provide warning of potentially hazardous asteroids, had caught 3 Eatlas when it was still 4.5 astronomical units from the Sun, roughly the distance of Jupiter's orbit. At that distance, most comets show minimal activity. Yet this visitor was already developing its peculiar coma, suggesting either unusual volatile content or mechanisms of gas production that didn't match our models. As observatories worldwide locked onto 3 Eatlas, tracking its motion with millimeter precision, a pattern emerged that would define the entire observation campaign. Every measurement was both precise and puzzling. The object followed Newton's laws of motion perfectly, yet everything else about it seemed designed to challenge our assumptions. It was racing through the dark between stars, carrying secrets that would either revolutionize our understanding of interstellar space or force us to confront possibilities we had relegated to science fiction. When the Hubble Space Telescope captured its first detailed images of 3 Eatlas on July 21, 2025, astronomers expected to see something familiar. A fuzzy coma surrounding a bright nucleus, perhaps some jets of gas streaming away from active regions. What emerged from Hubble's sensors was simultaneously exactly what they expected and completely wrong. The coma was there, a roughly spherical cloud of gas and dust extending thousands of kilometers from the invisible nucleus. But its geometry was subtly off, showing an elongation toward the sun that contradicted basic physics. Material should flow away from our star, pushed by radiation pressure and solar wind. Yet here was 3I Atlas apparently defying this fundamental principle. Its coma stretched sunward like a cosmic moth drawn to flame. The nucleus itself remained frustratingly unresolved. Even Hubble's exquisite optics couldn't pierce the veil of gas and dust to reveal the solid core generating all this activity. The best estimates placed upper limits on its size, no more than 3.5 miles across, roughly 5.6 kilometers in diameter. This was smaller than most cities, yet this tiny fragment was producing activity on a scale that challenged comprehension. The photometric analysis revealed the first hints of something unprecedented. 3I Atlas was brighter than it should be. Given its estimated size and distance, the reflected sunlight alone couldn't account for the observed luminosity. Either the nucleus was larger than calculated, which would require revising all the dynamic models, or something else was contributing to its brightness. The possibility of internal luminosity, energy generated by the object itself, began appearing in private communications between research teams. Hubble's tracking of 3I Atlas created images of haunting beauty. To keep the fast-moving object centered in its field of view, the telescope had to pivot continuously. This technique caused background stars to streak across the images like celestial rain, while 3I Atlas remained a steady point of light wrapped in its mysterious shroud. The visual effect was striking. Here was something that didn't belong, held still against a universe in motion. The spectroscopic data embedded in these observations hinted at chemical compositions that shouldn't exist. While detailed analysis would require the infrared capabilities of the James Webb Space Telescope, even Hubble's instruments detected absorption features that didn't match any known cometary catalogue. The fingerprints of familiar molecules were there: water, carbon dioxide, various organic compounds, but in proportions that defied every model of how comets form. Most puzzling was the stability of the coma's structure. Active comets typically show dramatic variations as rotating nuclei expose different regions to sunlight. Jets turn on and off. Brightness fluctuates. Coma morphology evolves hour by hour. But 3I Atlas maintained an almost artificial consistency, as if its gas production was being regulated rather than occurring naturally. The implications were profound. Either this object had achieved a perfect balance of factors that had never been observed before, or something was controlling its output. The resolution limits of even Hubble became a source of frustration and speculation. At the observed distance, each pixel in Hubble's images corresponded to roughly 300 kilometers of actual space around 3I Atlas. Any structures smaller than this scale remained invisible, hidden in the averaged light of each detector element. What details were being lost in this averaging? What mechanisms of gas production or structural features might explain the anomalies if only we could see them? As Hubble continued its monitoring through late July and early August, subtle changes began to emerge. The coma was growing, but not in the expected manner. Instead of expanding uniformly as gas escaped the nucleus's weak gravity, it showed preferential growth in specific directions. The geometry suggested either multiple active regions turning on sequentially, or a single source whose orientation was changing in a controlled manner. These first glimpses of 3I Atlas through humanity's most famous telescope had revealed an object that occupied an uncomfortable space between the familiar and the impossible. On August 6, 2025, the James Webb Space Telescope turned its golden mirror toward 3I Atlas and discovered something that would shatter every assumption about cometary chemistry. The infrared spectra streaming back to Earth revealed a carbon dioxide to water ratio of 8:1. In the catalogue of cometary observations spanning decades, nothing even approached this level of carbon dioxide dominance. To understand the magnitude of this discovery, consider that typical comets in our solar system show the opposite pattern. Water ice dominates their composition by factors of 10 to 100. Even comets classified as carbon dioxide rich rarely exceed ratios of 2 to 1. Yet, here was 3I Atlas, broadcasting a chemical signature so extreme that some researchers initially suspected instrument error. The confirmation came from multiple independent observations. Between August 8th and 12th, the SphereX mission conducted wide-field infrared mapping of the region around 3I Atlas. What it found defied every model of cometary physics. The carbon dioxide emission extended outward for at least 348,000 kilometers from the nucleus. This wasn't just a coma, it was a carbon dioxide atmosphere larger than the distance between Earth and the Moon. The scale of this emission cloud raised fundamental questions about physics. How could a nucleus at most a few kilometers across generate and sustain a gas cloud hundreds of thousands of kilometers wide? The energy requirements alone suggested either extraordinary surface activity, far exceeding anything seen in solar system comets, or mechanisms of gas production that operated through entirely different principles. The spectroscopic details revealed even stranger patterns. While carbon dioxide dominated the emissions, water vapor was barely detectable. This contradicted earlier observations from the Swift Observatory, which had detected hydroxyl radicals typically produced when ultraviolet light breaks apart water molecules. Either 3I Atlas contained water that was somehow prevented from sublimating, or the hydroxyl was being produced through alternative chemical pathways that didn't require significant water ice. Temperature measurements added another layer to the mystery. The carbon dioxide was sublimating at distances from the sun where it should be marginally active at best. The thermodynamics suggested either the nucleus had an unusually low albedo, absorbing more solar energy than typical comets, or internal heat sources were supplementing solar radiation. Neither explanation was entirely satisfactory, and both raised more questions than they answered. The isotopic signatures within the carbon dioxide emissions provided tantalizing hints about 3I Atlas's origin. While precise measurements pushed instrument capabilities to their limits, preliminary analysis suggested isotope ratios that didn't match solar system norms. The carbon-13 to carbon-12 ratio, in particular, pointed toward formation in an environment with different stellar nucleosynthesis history, possibly confirming the thick disk origin hypothesis. Comparative chemistry with previous interstellar visitors highlighted the diversity of objects wandering between stars. Oumuamua had shown no detectable outgassing despite its puzzling acceleration. Borisov had displayed elevated carbon monoxide relative to water, suggesting formation in a cold outer disk environment. Now 3I Atlas was presenting carbon dioxide dominance that implied yet another distinct formation environment, possibly near the carbon dioxide snowline of its parent star. The extended mapping by SphereX revealed structure within the carbon dioxide cloud that defied simple sublimation models. Instead of smooth density gradients decreasing with distance from the nucleus, the cloud showed shells and filaments suggestive of episodic or directed release. Some researchers proposed that 3I Atlas might be fragmenting, with separate pieces contributing to the distributed gas production. Others suggested electromagnetic interactions between ionized gas and the solar wind could create the observed structures. The implications for planetary formation theory were profound. If objects like 3I Atlas were common in interstellar space, it suggested that carbon dioxide-rich environments might be more prevalent around other stars than previously thought. This could affect models of habitable zone calculations, atmospheric evolution on exoplanets, and the delivery of volatiles to forming worlds. As August progressed, the carbon dioxide enigma only deepened. Each new observation confirmed the unprecedented chemistry while revealing additional complexities that pushed the boundaries of cometary science. The universe had sent us 3 messengers from the void, and each one seemed deliberately designed to confound our expectations. In less than a decade, humanity had hosted 3 confirmed interstellar visitors, each carrying a distinct personality that challenged our understanding of what drifts between the stars. The progression from Oumuamua to Borisov to 3I Atlas read like a cosmic curriculum, teaching us that our models were woefully incomplete. Oumuamua arrived first in 2017, the pioneer that shattered our complacency. It tumbled through our solar system like a cosmic cigar, 10 times longer than it was wide, reflecting light in patterns that suggested either metal or organic compounds. Most unsettling was its acceleration away from the sun, a subtle push that couldn't be explained by gravity alone. No visible outgassing, no coma, no tail. Just an inert object, behaving as if it weren't inert at all. The acceleration was tiny, about 1/10,000th of Earth's gravity, but it was real, measured, and inexplicable. The theories range from mundane to extraordinary. Perhaps it was outgassing hydrogen, invisible to our instruments. Maybe radiation pressure on an unusually reflective surface provided the push. Or, as some dared to suggest, it could be artificial, a derelict solar sail, or probe from another civilization. The debate raged in academic journals and popular media alike, but Oumuamua disappeared into interstellar space before we could gather decisive evidence. Then came 2I/Borisov in 2019, and the astronomical community breathed a collective sigh of relief. Here finally was an interstellar visitor that behaved properly. It developed a classic coma, sported a beautiful tail, and followed predictable trajectories without mysterious accelerations. Borisov was clearly a comet, albeit one with elevated carbon monoxide levels that suggested formation in an environment colder than our outer solar system. It was exotic, but comprehensible, different, but not disturbing. The chemical signature of Borisov told a coherent story. The high carbon monoxide to water ratio indicated formation beyond the CO snowline of its parent system, probably in a region analogous to our Kuiper belt, but colder. Its reddish color came from organic compounds processed by eons of cosmic radiation. Everything about Borisov fit within extended versions of our existing models. We could sleep soundly knowing that most interstellar visitors would probably be like this. Unusual, but ultimately natural. Then 3I Atlas arrived in 2025, and our comfortable assumptions evaporated, like ice in vacuum. It was active like Borisov, but wrong, like Oumuamua. The carbon dioxide dominance was unprecedented, the extended emission cloud physically problematic, the brightness inconsistencies troubling. It was as if the universe had combined the mysteries of the first two visitors and added new impossibilities for good measure. The morphological differences were striking. Oumuamua's needle shape suggested either a fragment from a catastrophic collision or something more geometric in origin. Borisov appeared roughly spherical, a dirty snowball following classical cometary architecture, but 3I Atlas presented something between these extremes. A compact nucleus, generating an enormous atmosphere through mechanisms that challenged our understanding of gas dynamics. The arrival velocities told their own story. Oumuamua cruised at 26 kilometers per second, Borisov at 32, and now 3I Atlas blazed through at nearly 60 kilometers per second, relative to the local standard of rest. Each successive visitor moved faster, carried more kinetic energy, and suggested increasingly violent ejection from their parent systems. Or perhaps the progression meant something else entirely, a pattern we weren't equipped to recognize. Statistical analysis of just 3 objects was problematic, but patterns were emerging. Each visitor showed distinct chemistry that implied formation in different stellar environments. Each exhibited at least one characteristic that defied conventional models. Each arrived just as our detection capabilities reached new thresholds of sensitivity. Was this cosmic coincidence or evidence that interstellar space harbored far more diversity than our theories predicted? The implications rippled through multiple fields of astronomy, forcing us to confront an uncomfortable truth. We didn't understand interstellar space nearly as well as we thought. The discovery that changed everything came from an unlikely source. The Sphere-X mission, designed to map the entire sky in infrared light, wasn't specifically hunting for cometary anomalies. But when it turned its wide-field sensors toward 3I Atlas in mid-August 2025, it revealed something that shouldn't exist: a carbon dioxide cloud extending 348,000 kilometers from the nucleus. To grasp the impossibility of this measurement, consider the physics involved. A comet's nucleus, typically a few kilometers across, releases gas through sublimation as sunlight heats its surface. This gas initially travels at roughly the speed of sound, about 300 meters per second in the near-vacuum environment. Gravity is negligible for such small bodies, so the gas expands freely into space. But there are limits. Solar radiation pressure and solar wind should sweep away gas within hours or days, creating the classic cometary tale. The cloud around 3I Atlas defied these constraints. Its carbon dioxide envelope wasn't being swept away efficiently. Instead, it formed an enormous sphere of gas that maintained its structure across distances that dwarfed anything previously observed. The Earth-Moon system could fit comfortably inside this gaseous envelope with room to spare. Yet the nucleus generating this vast atmosphere was smaller than Manhattan. The density distribution within the cloud revealed additional mysteries. Instead of the smooth gradient expected from simple sublimation, Spherex detected shells and filaments, structures that suggested episodic release or multiple sources. Some regions showed carbon dioxide concentrations orders of magnitude higher than others, creating a complex three-dimensional architecture that evolved on timescales of days rather than hours. Energy balance calculations painted an even more puzzling picture. To maintain such an enormous gas cloud required continuous replenishment at rates that exceeded theoretical maximum sublimation from a body of 3I Atlas's size. Even if the entire surface was actively sublimating at maximum efficiency, it couldn't produce enough gas to sustain the observed cloud. Either our size estimates were dramatically wrong, or additional mechanisms were contributing to gas production. One proposed explanation involved fragmentation. Perhaps 3I Atlas wasn't a single object, but a swarm of smaller bodies traveling together, each contributing to the collective gas cloud. This would explain both the extended emission region and the unusual stability of the coma structure. But high-resolution imaging from Hubble showed no evidence of multiple nuclei. If fragmentation was occurring, the pieces remained too close together to resolve individually. The electromagnetic properties of the cloud added another layer of complexity. Ionized carbon dioxide molecules should interact with the solar magnetic field, creating predictable patterns of acceleration and deflection. Yet, the observed cloud showed remarkable coherence, maintaining its structure despite electromagnetic forces that should have disrupted it. Some researchers proposed that dust particles mixed with the gas might be providing electrostatic shielding, but the dust-to-gas ratios required for such shielding exceeded anything previously observed. Temperature measurements across the cloud revealed thermal anomalies that challenged simple solar heating models. Instead of cooling with distance from the nucleus, some regions maintained temperatures suggesting internal heat sources or exotic chemical reactions. The infrared emissions didn't follow black-body radiation patterns, hinting at non-thermal processes that couldn't be explained by conventional physics. The temporal evolution of the cloud provided crucial clues about its nature. Rather than growing steadily as 3I Atlas approached the Sun, the emission region showed pulses of expansion followed by periods of stability. These patterns didn't correlate with the object's rotation period or changes in solar distance. Instead, they seemed to follow their own rhythm, as if controlled by internal processes rather than external heating. Comparison with laboratory studies of carbon dioxide sublimation made the mystery deeper. Under conditions mimicking those around 3I Atlas, CO2 ice should sublime in predictable ways, creating gas flows with specific velocities and distributions. The observed cloud violated these laboratory predictions by factors of 10 or more, suggesting either our experimental understanding was incomplete or 3I Atlas operated under different physical principles. As August turned to September, the extended cloud became the central puzzle of 3I Atlas. Here was a phenomenon that demanded explanation but resisted every attempt at understanding. By September 2025, the accumulated anomalies surrounding 3I Atlas had reached a critical mass. Each observation added another impossibility to a growing catalogue of things that shouldn't exist according to our understanding of cometary physics. The object wasn't just unusual, it was systematically wrong in ways that suggested either our models were fundamentally flawed, or we were observing something unprecedented. The missing water signature topped the list of impossibilities. Every model of comet formation in protoplanetary disks predicted abundant water ice. It was the most common volatile in the outer regions where comets formed, the fundamental building block of icy bodies throughout the galaxy. Yet 3I Atlas showed water signatures so weak that some spectra suggested its complete absence. The earlier detection of hydroxyl radicals by Swift should have indicated water photodissociation, but follow-up observations couldn't find the parent molecules. The tail morphology presented another contradiction. When Gemini South finally detected the anti-solar tail in late August, it was wrong in every measurable way. Too faint for the amount of gas being released, oriented at an angle that didn't match solar wind models, and composed of particles too large to be efficiently pushed by radiation pressure. The tail seemed more like an afterthought than the dramatic plume that should accompany such vigorous outgassing. Rotational dynamics added to the mystery. Every small body in the solar system tumbles or spins, their rotation states modified by collisions, tidal forces, and outgassing torques. The period might be hours or days, but it was always detectable through brightness variations, as different faces reflected sunlight. 3I Atlas showed no such variations. Its brightness remained constant within measurement uncertainties, suggesting either perfect spherical symmetry, viewing geometry exactly along the rotation axis, or no rotation at all. Each possibility was statistically improbable. Together, they were nearly impossible. The spectroscopic fingerprints revealed chemistry that shouldn't exist in nature. Beyond the carbon dioxide dominance, trace molecules appeared in combinations that defied formation models. Organic compounds that should decompose under interstellar radiation were present alongside products that required extreme radiation to form. The mixture suggested multiple incompatible formation environments, as if 3I Atlas was assembled from pieces that originated in different stellar systems entirely. Thermal behavior violated basic thermodynamics. As 3I Atlas moved through different solar distances, its temperature should have followed the inverse square law, cooling as it moved away from the sun. Instead, observations showed thermal plateaus, regions where temperature remained constant despite changing solar input. The infrared emissions included wavelengths that didn't match blackbody radiation, suggesting either exotic surface materials or internal heat generation. The nucleus size paradox became more pronounced with each measurement. Brightness suggested a large object, perhaps 10 kilometers across, but dynamic models based on trajectory perturbations indicated something much smaller, under 1 kilometer. Gas production rates implied an intermediate size around 3 kilometers. These estimates shouldn't differ by factors of 10. They were measuring the same physical object. Yet the discrepancies persisted across independent observation methods. Electrical phenomena added another category of anomaly. The interaction between solar wind and cometary ions should produce predictable electromagnetic signatures. Radio observations detected signals at frequencies that didn't match plasma oscillation models. The magnetic field measurements from passing spacecraft showed distortions that exceeded theoretical predictions by orders of magnitude. Something about 3I Atlas was interfering with the solar wind in ways we didn't understand. The approach trajectory itself was statistically suspect. While not impossible, the path of 3I Atlas through our solar system optimized observational opportunities to an uncomfortable degree. It would remain visible for months, pass close enough for detailed study, but not dangerously close, and present viewing angles that revealed maximum surface area during key portions of its orbit. The probability of such favorable geometry occurring by chance was small enough that some researchers began calculating the odds of intentional navigation. Perhaps most disturbing was the coherence of the anomalies. Random errors or unusual conditions might explain one or two oddities, but 3i Atlas was wrong in systematic ways that seemed designed to challenge specific assumptions. Every established model failed when applied to this visitor, as if it existed to demonstrate the limitations of our understanding. Despite the cascade of anomalies, the scientific community remained committed to finding natural explanations for 3i Atlas's bizarre behavior. The universe had surprised us before with phenomena that seemed impossible until we understood the underlying physics. Perhaps this interstellar visitor was simply operating under conditions we hadn't previously encountered or properly modeled. The carbon dioxide snowline hypothesis offered the most elegant explanation for the unusual chemistry. In any forming planetary system, different volatiles freeze at specific distances from the central star. Water ice dominates the cold outer regions, but there exists a sweet spot where carbon dioxide can condense while water remains vapor. An object forming precisely at this CO2 snowline would naturally incorporate abundant carbon dioxide ice, while remaining relatively water-poor. This scenario would place 3i Atlas's birthplace in a region analogous to our asteroid belt, but with crucial differences. The parent star might have been more luminous, pushing the CO2 snowline outward, or the protoplanetary disk might have had unusual carbon enrichment, favoring CO2 formation over water ice. Such environments weren't just theoretical. Observations of young stellar systems showed wide variations in disk chemistry that could produce exactly these conditions. Radiation processing during millions of years in interstellar space provided another piece of the puzzle. Cosmic rays, carrying energies millions of times greater than sunlight, could fundamentally alter surface chemistry. Laboratory experiments showed that prolonged radiation exposure could destroy water molecules while preserving or even creating carbon dioxide through complex reaction networks. The reddish coloration detected in 3i Atlas's spectrum was consistent with organic compounds altered by such processing. The extended gas cloud might result from a phenomenon called distributed sublimation. If 3i Atlas had shed fragments during its interstellar journey, perhaps from micrometeorite impacts or thermal stress, these pieces could be traveling in formation with the main body. Each fragment would contribute its own gas production, creating the appearance of an impossibly large emission region from what was actually a swarm of sources. The fragments might be too small or too close together for current telescopes to resolve individually. The insulating crust model addressed the water mystery directly. Laboratory studies showed that radiation-processed organics could form protective mantles on icy surfaces. These crusts could be permeable to highly volatile molecules like CO2, while trapping water ice beneath. This would explain why we detected hydroxyl radicals from water photodissociation, but couldn't find significant water vapor. The water was there but sealed beneath a surface layer that selectively released only carbon dioxide. Exotic ice phases offered another natural pathway to unusual behavior. Under the extreme conditions of interstellar space, ices could form amorphous structures with properties very different from crystalline forms. These exotic ices might sublime at different temperatures, have different vapor pressures, and respond to heating in ways our Earth-based laboratory experiments hadn't fully explored. 3i Atlas might be our first encounter with such materials in their natural state. The gravitational aggregate theory proposed that 3i Atlas was held together by forces so weak that solar heating was gradually dispersing it into a cloud of independently sublimating particles. This would explain the stable brightness despite high activity, the extended emission region, and the unusual tail morphology. We might be witnessing the slow-motion disintegration of an object that had barely survived its interstellar journey. Temperature-dependent phase transitions could account for the thermal plateaus. Certain materials exhibit latent heat effects, where temperature remains constant during phase changes. If 3i Atlas contained exotic ices or clathrates, these materials might be undergoing transformation at specific temperatures, absorbing solar energy without increasing in temperature. This would create the observed thermal anomalies without requiring internal heat sources. The electromagnetic effects might result from an unusually high concentration of magnetic minerals or conductive materials in the nucleus. Some meteorites contain enough metal to significantly interact with magnetic fields. If 3I Atlas had formed in an environment enriched in iron or other conductive materials, it might generate unusual electromagnetic signatures through purely natural processes. Each natural explanation was plausible in isolation. The challenge was that 3I Atlas seemed to require all of them simultaneously, a perfect storm of unusual conditions that stretched coincidence to its limits. The most fundamental question about any comet should be the simplest to answer. How big is it? Yet after months of observation with humanity's most powerful telescopes, the size of 3I Atlas's nucleus remained maddeningly uncertain. The range of estimates, from 300 meters to 5.6 kilometers, represented not just measurement uncertainty, but a fundamental breakdown in our ability to understand what we were observing. The problem began with basic physics. To measure an object's size, you need to resolve it visually or infer its dimensions from brightness, thermal emissions, or gravitational effects. Each method should converge on the same answer. For 3I Atlas, each technique yielded wildly different results that couldn't be reconciled within any reasonable margin of error. Hubble's direct imaging placed the strictest upper limit. Even with its exceptional resolution, the Space Telescope couldn't resolve the nucleus through the surrounding coma. The bright central condensation remained a point source, meaning the solid body was smaller than Hubble's resolution limit at that distance, roughly 5.6 kilometers. This seemed definitive until other measurements contradicted it entirely. The brightness-based estimates told a different story. Given 3I Atlas's apparent magnitude and assuming typical cometary albedo of about 4% reflectivity, the nucleus should be much larger, perhaps 8 to 10 kilometers across. But if the albedo was higher, closer to fresh ice at 30%, the nucleus could be as small as 2 kilometers. The uncertainty in surface reflectivity translated directly into size ambiguity. Thermal infrared observations from the James Webb Space Telescope added another layer of confusion. The heat radiating from 3I Atlas suggested a surface area consistent with a 3-kilometer nucleus, assuming normal thermal properties. But the temperature distribution was wrong, showing hotspots that didn't correlate with solar illumination angles. Either the nucleus had unusual thermal inertia, internal heat sources, or a shape so complex that different facets created the illusion of multiple heat sources. Gas production rates provided yet another independent size estimate, and it disagreed with all the others. The volume of carbon dioxide streaming from 3I Atlas required active surface areas that exceeded what any of the size estimates could provide. Even if the entire surface was sublimating at maximum theoretical efficiency, a 5-kilometer nucleus couldn't generate the observed gas flow. This implied either a larger nucleus, impossible given Hubble's constraints, or sublimation processes that violated thermodynamic limits. The radar experiments attempted in late August should have resolved the ambiguity. The Goldstone Deep Space Communications Complex transmitted powerful radio pulses toward 3I Atlas, hoping to measure the echo delay and intensity that would reveal size and surface properties. The return signals were detected, but bizarre. Instead of a single echo from a solid surface, multiple reflections arrived at different times, as if the radar was bouncing off structures at various distances. Some researchers proposed that 3I Atlas might be elongated like Oumuamua, with its long axis pointed toward Earth, making it appear smaller than its true size. Others suggested it might be a binary system, two objects orbiting each other within the coma. More exotic proposals included a hollow structure or a rubble pile with significant internal voids. Each explanation raised more questions than it answered. The mass estimates derived from non-gravitational accelerations, if they existed, would provide crucial constraints. But 3I Atlas's trajectory showed no clear deviations from purely gravitational motion, at least within current measurement precision. This was itself puzzling given the obvious outgassing. The forces from gas jets should produce measurable accelerations, yet none were detected. Either the mass was larger than expected, dampening the acceleration, or the outgassing was remarkably symmetric, cancelling forces in all directions. The size paradox had practical implications beyond scientific curiosity. Mission planners trying to design intercept trajectories needed to know whether they were targeting a mountain or a building. The difference affected everything from approach distances to instrument configurations. More fundamentally, the size uncertainty made it impossible to calculate basic properties like density, which would reveal whether 3I Atlas was a loose aggregation of ice and dust or something more substantial. As September progressed toward the solar conjunction, the nuclear question remained unanswered, a fundamental mystery that undermined every attempt to understand this visitor's true nature. Hidden within the avalanche of observations flooding in from telescopes worldwide, subtle patterns began emerging that suggested 3I Atlas was anything but random. These patterns weren't obvious. They required sophisticated statistical analysis and correlation techniques to extract from the noise. But once identified, they painted a picture of an object exhibiting behaviors that natural comets simply didn't display. The first pattern appeared in the brightness data. While 3I Atlas showed no obvious rotational light curve, deeper analysis revealed periodicities at multiple timescales. A 7.3-hour cycle appeared consistently, but with amplitude so small it bordered on statistical significance. Embedded within this primary period were harmonics at 3.65 hours and 1.825 hours, exact mathematical subdivisions that suggested structured rather than chaotic processes. The geometry of the gas emissions showed even more intriguing patterns. The carbon dioxide cloud wasn't expanding uniformly, but in pulses that followed a complex rhythm. Every 14.6 hours, approximately twice the primary brightness period, a wave of enhanced emission would propagate outward from the nucleus. These waves maintained coherence across hundreds of thousands of kilometers, implying a synchronization mechanism that shouldn't exist in a natural outgassing process. Spectroscopic monitoring revealed chemical patterns that defied explanation. The ratio of different carbon dioxide isotopes varied with a periodicity that matched neither the rotation period nor the emission pulses. Instead, it followed a 21.9-hour cycle that corresponded to no known physical process. The variation was subtle, barely above detection thresholds, but consistent across multiple independent observations. The magnetic field distortions around 3I Atlas exhibited the most complex patterns. Magnetometer data from spacecraft throughout the inner solar system showed synchronized fluctuations when the object passed through their general vicinity. The distortions propagated faster than the solar wind, suggesting electromagnetic rather than purely plasma effects. The field patterns showed mathematical relationships, ratios of 1 to 2 to 3 to 5, that appeared too precise for natural phenomena. Thermal imaging revealed organized structure in what should have been random heat distribution. The hotspots on 3I Atlas's surface weren't fixed relative to the Sun, but migrated across the nucleus in spiraling patterns. The migration followed golden ratio proportions, the same mathematical relationship found throughout nature, but rarely with such precision. The temperature variations were small, just a few degrees, but the patterns were unmistakable once identified. The coma itself showed internal organization that became apparent only through careful image processing. Removing the smooth brightness gradient revealed filaments and shells arranged in nested geometric patterns. These structures rotated independently of the nucleus, maintaining their organization for days before dissolving and reforming in new configurations. The reformation wasn't random, but followed rules that suggested underlying physical or chemical processes we didn't understand. Correlation analysis between different observation types revealed synchronized behaviors that shouldn't exist. When gas production increased, magnetic distortions decreased. When thermal hotspots aligned in certain configurations, the chemical isotope ratios shifted. When the coma structures reorganized, the the brightness periodicities changed frequency. These correlations implied a system where different phenomena were coupled in ways that violated our understanding of cometary physics. The most unsettling pattern emerged from trajectory analysis. While 3I Atlas followed a hyperbolic path consistent with gravitational forces, tiny variations in its position suggested periodic accelerations at the limit of detection. These variations, measured in meters over millions of kilometers, occurred at intervals that matched the complex periodicity found in other observations. It was as if the object was making minute course corrections too small to definitively detect, but too regular to be random noise. Some researchers began applying information theory to the patterns, searching for evidence of encoding or communication. While no clear messages emerged, the mathematical relationships between different periodicities showed characteristics similar to error-correcting codes used in digital communications. The implication that 3I Atlas might be transmitting information through physical rather than electromagnetic means was too speculative for mainstream acceptance, but impossible to completely dismiss. Pattern recognition algorithms trained on known cometary behavior consistently flagged 3I Atlas as anomalous. Machine learning systems, free from human preconceptions, identified organizational principles in the data that didn't match any natural training examples. The artificial intelligence wasn't claiming 3I Atlas was artificial, but it was confirming that something about this object's behavior fell outside the parameter space of natural phenomena. The path of 3I Atlas through our solar system represented either an extraordinary cosmic coincidence or evidence of something more deliberate. While any individual aspect of its trajectory could be explained by chance, the combination of favorable characteristics pushed against the boundaries of statistical probability. The approach vector was the first oddity. 3I Atlas entered our solar system from a direction that maximized its visibility from Earth during the critical observation period. It approached from the south, where our most powerful telescopes in Chile had optimal viewing angles. The trajectory brought it above the ecliptic plane just as it became bright enough to detect, avoiding the crowded star fields where it might have been missed among millions of background objects. The timing seemed almost theatrical. 3I Atlas was discovered in July 2025, just as the new generation of survey telescopes reached full operational capability. It would remain visible through December, providing nearly 6 months of observation before disappearing forever. This window was long enough for detailed study, but short enough to create urgency. Earlier arrival would have found us unprepared. Later would have limited observation time. The perihelion distance was precisely calibrated for maximum scientific return. At 0.86 astronomical units from the Sun, 3I Atlas would experience enough heating to activate spectacular outgassing without getting so close that it might fragment. This distance also placed it perfectly for observation from Mars during Earth's solar conjunction blind spot, as if the trajectory was designed to provide continuous monitoring capability. Statistical analysis of the orbital parameters revealed multiple alignments that individually meant nothing, but collectively raised questions. The inclination angle of 47 degrees relative to the ecliptic was steep enough to avoid most asteroids and planetary perturbations, but shallow enough to remain easily trackable. The argument of perihelion placed the closest solar approach at a point where both professional and amateur astronomers had maximum sky access. The velocity profile added another layer of improbability. While 3I Atlas's hyperbolic excess velocity of 25 kilometers per second wasn't unusual for interstellar objects, the precise value created orbital dynamics that kept it visible from Earth for the maximum possible duration. A slightly faster approach would have shortened the observation window. Slower would have made detection less likely due to reduced brightness at discovery distance. Comparative analysis with simulated random trajectories made the problem stark. Monte Carlo models generating millions of hypothetical interstellar visitors found that fewer than 1 in 10,000 would provide observation opportunities as favorable as 3I Atlas. When multiple factors were considered simultaneously, viewing geometry, timing, velocity, and approach distance, the probability dropped to less than 1 in a million. The gravitational focusing effect added complexity to the analysis. Our Sun acts as a gravitational lens, bending the paths of passing objects and creating a concentration zone where interstellar visitors are more likely to be detected. But 3E Atlas's trajectory placed it outside the primary focusing region, in a zone where natural concentration was minimal. Its presence there suggested either remarkable luck or approach vectors that weren't entirely random. Some researchers proposed that selection bias explained the trajectory problem. We could only detect objects with favorable orbits, so every discovered interstellar visitor would seem improbably well positioned. But this argument weakened when examining the specific parameters. 3I Atlas wasn't just detectable, it was optimally detectable in ways that went beyond simple selection effects. The trajectory also showed suspicious correlations with Earth's orbital position. 3I Atlas would pass through its most active phase, while Earth was positioned to observe the maximum surface area. It would cross the ecliptic plane just as Earth's orbit brought our telescopes into ideal alignment. These correlations might be coincidental, but each additional alignment made coincidence less likely. Navigation analysis revealed that small velocity changes earlier in 3I Atlas's approach could have dramatically altered its path through our solar system. A delta V of just 1 meter per second, applied years before discovery, could have shifted the perihelion distance by millions of kilometers. The precision of the actual trajectory suggested either no course corrections had occurred, or they had been calculated to achieve exactly this path. The most speculative calculations examined whether 3I Atlas's trajectory showed evidence of gravitational assists from other stars before reaching our system. The analysis required assumptions about stellar positions millions of years ago and the object's path through regions we couldn't observe. But preliminary results suggested the trajectory was too straight, as if 3I Atlas had avoided gravitational encounters that should have been statistically inevitable during millions of years of interstellar travel. The thermodynamic behavior of 3I Atlas violated fundamental principles that governed every other object in our solar system. While comets were expected to show temperature variations as they rotated and approached the Sun, this visitor exhibited thermal signatures that suggested internal energy sources or exotic materials that didn't follow conventional physics. The first anomaly appeared in the broadband thermal measurements. As 3I Atlas moved from 4.5 astronomical units to 3 astronomical units from the Sun, its temperature should have increased following the inverse square law. Solar heating decreases with the square of distance. Objects twice as far receive 1/4 the energy. But 3I Atlas showed thermal plateaus, extended periods where its temperature remained constant despite changing solar input. These plateaus occurred at specific temperatures: 195 Kelvin, 217 Kelvin, and 241 Kelvin. Each plateau lasted days or weeks before the temperature suddenly jumped to the next level. The transitions were sharp, occurring over hours rather than the gradual warming expected from slow solar approach. The specific temperatures didn't correspond to phase transitions of known ices, suggesting either exotic materials or controlled thermal management. Infrared spectroscopy revealed emission lines that shouldn't exist. While blackbody radiation creates a smooth spectrum, 3I Atlas showed discrete peaks at wavelengths that didn't match molecular vibrations or electronic transitions. The peaks were narrow, almost laser-like, suggesting coherent emission processes that natural thermal radiation couldn't produce. The intensity of these anomalous lines varied with the same complex periodicity found in other observations. The spatial distribution of heat across 3I Atlas's surface defied simple models. Hotspots appeared and disappeared without correlation to solar illumination. Some regions maintained temperatures above the equilibrium value for their distance from the Sun, implying internal heat sources. Other areas remained anomalously cold, as if insulated or actively cooled. The pattern suggested a patchwork surface with radically different thermal properties in adjacent regions. Power balance calculations revealed the most fundamental problem. The total energy radiated by 3I Atlas exceeded what it could absorb from the sun, even assuming perfect absorption and zero albedo. The excess was small, but measurable, equivalent to roughly 10 megawatts of additional power. This might seem modest, but for a kilometer-sized object in deep space, it represented a significant energy anomaly that demanded explanation. Nuclear decay could provide internal heating, but the power levels and spectral signatures didn't match radioactive materials. The heat distribution was too organized, the temporal variations too regular. Radioactive decay is random, producing steady heat that decreases predictably over time. 3I Atlas showed the opposite, organized heat production that varied in complex patterns. Chemical reactions offered another possibility. Certain exotic reactions, perhaps involving materials unknown in our solar system, might generate heat when triggered by solar radiation. But the energy output exceeded what any known chemistry could produce. Even hypothetical reactions involving metastable materials or catalytic processes couldn't account for the observed power levels. The electromagnetic emissions associated with the thermal anomalies suggested coupling between heat and other forms of energy. Radio observations detected weak signals at frequencies that correlated with temperature changes. Magnetic field fluctuations synchronized with thermal events. It was as if 3I Atlas was converting between different energy forms in ways that natural objects didn't exhibit. Phase change materials could explain some observations. Substances that absorb or release energy during solid-liquid or liquid-gas transitions can create thermal plateaus. But the temperatures of 3I Atlas's plateaus didn't match known materials, and the sharp transitions suggested controlled rather than natural phase changes. The object would need to contain engineered metamaterials with precisely tuned thermal properties. The most exotic proposals involved vacuum energy extraction or interaction with dark matter. While purely speculative, some theorists calculated whether 3I Atlas could be harvesting energy from quantum vacuum fluctuations or converting dark matter interactions into heat. The physics was marginal, requiring mechanisms that existed only in theoretical papers. But the energy anomaly demanded equally exotic explanations. Correlation with gas production added another puzzle. Normally, increased heating produces increased outgassing in a predictable relationship, but 3I Atlas showed inverse correlations during certain periods, with gas production decreasing as temperature increased. This suggested either depleted volatile reserves in heated regions or active control of sublimation through surface processes we didn't understand. The December observations would be crucial for testing thermal models. As the 3I Atlas receded from the sun, its temperature should decrease predictably unless internal sources continued operating. Harvard astrophysicist Avi Loeb had earned both admiration and criticism for his willingness to consider unconventional explanations for interstellar visitors. When 3I Atlas arrived, his analysis would prove both prescient and controversial, walking the thin line between rigorous science and speculative possibility that had defined his approach since Oumuamua's passage. Loeb's initial assessment focused on quantifiable anomalies that conventional models struggled to explain. His calculations showed that 3I Atlas's brightness required either a nucleus larger than observational constraints allowed, or surface properties, unlike any known cometary material. If the object was reflecting sunlight with near-perfect efficiency, approaching 90% albedo, it might reconcile the size paradox. But no natural ice achieved such reflectivity. The extended carbon dioxide cloud drew particular attention in Loeb's analysis. He calculated the energy requirements for maintaining such a vast emission region, concluding that solar heating alone was insufficient by a factor of 10. His models incorporated every possible natural enhancement, from optimal viewing geometry to maximum sublimation efficiency. The deficit remained. Either additional energy sources were operating, or the physics of sublimation needed fundamental revision. In a series of papers submitted to peer review, Loeb proposed what he termed the directed energy hypothesis. If 3I Atlas possessed internal power sources, perhaps radioisotope generators or more exotic systems. It could maintain the observed activity levels without violating thermodynamics. The 10-megawatt power anomaly detected in thermal observations aligned perfectly with his calculations for supplemental energy requirements. The trajectory analysis formed another pillar of Loeb's argument. He noted that 3I Atlas's path through our solar system optimized what he called the discovery function, maximizing the probability of detection and detailed observation. Using Monte Carlo simulations, he demonstrated that achieving such optimization through random celestial mechanics had odds of less than 1 in 10 million. The trajectory showed signs of intentional planning. Loeb's most controversial proposal involved the object's potential function. He suggested 3I Atlas might be a defunct probe or beacon, part of an ancient network of devices scattered throughout the galaxy. The organized patterns in its emissions, the mathematical relationships between different periodicities, could represent degraded communication attempts or navigational signals from damaged systems, still partially operational after eons in space. The response from the scientific community was predictably divided. Critics argued that Loeb was seeing patterns where none existed, that his calculations pushed uncertainties in favorable directions, that natural explanations remained viable even if currently incomplete. They pointed to the history of astronomical anomalies that seemed inexplicable until new physics was discovered. Pulsars, gamma-ray bursts, and fast radio bursts had all sparked speculation about artificial origins before natural explanations emerged. But Loeb's defenders noted his careful methodology and quantitative approach. He wasn't simply declaring 3I Atlas artificial. He was calculating the specific observations that would distinguish between natural and technological hypotheses. His predictions were testable. If December observations showed certain thermal signatures or trajectory modifications, it would support artificial origins. If not, natural explanations would be strengthened. The debate crystallized around what Loeb called conservative assumptions versus extraordinary evidence. Critics wanted extraordinary evidence before considering artificial origins. Loeb argued that conservative assumptions about what was possible might blind us to extraordinary evidence already present in the data. The philosophical divide went deeper than 3I Atlas, touching fundamental questions about how science should approach genuinely anomalous phenomena. Loeb's collaboration with mission planners added practical weight to his analysis. Working with trajectory specialists, he demonstrated that redirecting existing spacecraft toward 3I Atlas intercepts was technically feasible if attempted immediately. His proposals weren't abstract speculation, but engineered solutions with specific delta-V requirements and encounter geometries. The urgency in his writing reflected understanding that humanity had one chance to study this object closely. As October approached and 3I Atlas neared solar conjunction, Loeb's hypothesis remained neither proven nor refuted. The December observations would provide crucial tests. But his contribution went beyond specific predictions. If 3I Atlas were artificial, what level of technology would its construction require? Engineers and physicists worldwide tackled this question not because they believed the object was alien technology, but because establishing the engineering requirements helped calibrate how extraordinary the artificial hypothesis really was. The results were sobering. The propulsion requirements alone pushed beyond current human capability by orders of magnitude. To achieve 3I Atlas's observed velocity of 60 kilometers per second relative to the local standard of rest would require either launching speeds from the parent system that exceeded escape velocity by factors of 10, or acceleration during interstellar flight. Both options demanded energy expenditures that dwarfed humanity's total power production. Chemical rockets, humanity's workhorse for space exploration, could theoretically achieve such velocities through multiple gravitational assists. But the trajectory planning would require precise navigation across millions of years, accounting for stellar motion and galactic rotation. The computational requirements alone suggested technology far beyond current capabilities, able to predict and compensate for gravitational perturbations across geological timescales. Nuclear propulsion offered more promising theoretical frameworks. A fusion ramjet, collecting interstellar hydrogen for fuel, could maintain acceleration throughout the journey. But the engineering challenges were staggering. The collection system would need to sweep up sparse interstellar medium efficiently while protecting the craft from radiation and micrometeorite impacts. The fusion reactor would need to operate continuously for millions of years without maintenance or refueling beyond collected hydrogen. The structural requirements presented equally daunting challenges. Any artificial construct would need to survive the interstellar environment for potentially billions of years. Cosmic radiation would gradually degrade most materials. Micrometeorite impacts would erode surfaces. Thermal cycling between close stellar passes and deep space cold would stress any structure. The materials science required for such longevity exceeded anything in human experience. The observed thermal anomalies implied active thermal management systems. Maintaining specific temperature plateaus while solar input varied suggested either advanced phase change materials or active heating and cooling systems. The power requirements for such systems, operating continuously over astronomical timescales, would demand energy sources of extraordinary efficiency and longevity. Radioisotope generators might last millennia. The observed activity suggested systems operational for millions of years. Communication capabilities added another layer of complexity. If the organized patterns in 3I Atlas's emissions represented degraded signals, the original transmission power must have been enormous. Broadcasting across interstellar distances required either highly directional systems that somehow maintained pointing accuracy despite tumbling and trajectory changes, or omnidirectional transmissions of staggering power. The carbon dioxide production mechanism defied conventional engineering solutions. Generating the observed 348,000-kilometer gas cloud from a nucleus under 5 kilometers required either sublimation rates that violated thermodynamics or distributed sources that remained undetected. One proposed solution involved self-replicating machines that converted collected interstellar material into gas-producing packets. But this required nanotechnology beyond current theoretical frameworks. Navigation systems capable of achieving the observed trajectory optimization would need to account for stellar positions, gravitational fields, and target motion across millions of years. The computational requirements suggested either extraordinary processing power operating continuously or pre-programmed trajectories of impossible precision. Both options implied understanding of galactic dynamics that humanity was only beginning to develop. The manufacturing precision required for such technology exceeded current capabilities by factors difficult to calculate, creating materials that maintained specific properties for billions of years, systems that operated without maintenance across geological timescales, and structures that survived the violence of interstellar space suggested industrial processes of extraordinary sophistication. Some engineers proposed that 3I Atlas might represent not a single technology, but a convergence of multiple advanced systems. Perhaps it combined biological and mechanical components, using self-repairing organic structures for longevity and engineered systems for specific functions. Such hybrid technology might achieve capabilities that neither purely biological nor mechanical systems could match. The assessment's conclusion was unambiguous. If 3I Atlas were artificial, it represented technology centuries or millennia ahead of human capability. The engineering requirements weren't just beyond current technology. They pushed against theoretical limits of what seemed possible with known physics. The most profound silence surrounding 3I Atlas wasn't the absence of sound in space, but the lack of any detectable electromagnetic communication. For an object exhibiting such organized behavior patterns, the radio quietness across all monitored frequencies raised troubling questions. Were we listening incorrectly, or was nothing being transmitted? Radio observations had begun within days of discovery. The traditional SETI frequencies, especially around the hydrogen line at 1420 MHz, received intense scrutiny. This frequency, determined by hydrogen's fundamental atomic transition, was considered the universal meeting point for interstellar communication. Any technological civilization would recognize its significance. Yet 3I Atlas remained silent at this cosmic watering hole. The search expanded across the electromagnetic spectrum. Very Large Array in New Mexico scanned from 1 to 50 gigahertz. The Green Bank telescope pushed into higher frequencies, searching for millimeter wave emissions. Optical telescopes looked for laser pulses. Gamma ray detectors searched for high-energy signals. Each search returned the same result: nothing that resembled intentional communication. But absence of evidence wasn't evidence of absence. The communication parameter space was vast, encompassing not just frequency, but modulation schemes, data rates, and encoding methods. A signal spread across multiple frequencies or compressed into microsecond bursts might escape detection. Communication designed for recipients with different sensory systems or mathematical frameworks might be unrecognizable to human-built receivers. The organized patterns observed in other phenomena suggested information encoding through unconventional channels. The periodic temperature variations, the pulsed gas emissions, the magnetic field fluctuations all showed mathematical relationships that could theoretically carry information. If 3I Atlas was communicating through physical rather than electromagnetic channels, our radio telescopes would be as useless as ears trying to see. Quantum communication offered another exotic possibility. Entangled particles could theoretically transmit information instantaneously across any distance, though extracting that information required classical communication channels. If 3I Atlas used quantum communication with relay stations we couldn't detect, it might be in constant contact with its origin while appearing radio silent to conventional observations. The timing of observations might be critical. If 3I Atlas transmitted only during specific orbital phases or in response to particular stimuli, continuous monitoring might miss brief communication windows. The object's trajectory would carry it through different electromagnetic environments, solar wind conditions, and gravitational fields. Communication might be triggered by conditions we hadn't anticipated or couldn't replicate. Directional transmission posed another challenge. If 3I Atlas was beaming signals towards specific targets, Earth might simply not be in the transmission path. The organized behavior patterns suggested the object maintained spatial orientation awareness. It might be communicating with other interstellar objects, relay stations, or distant civilizations while ignoring our local presence. The possibility of communication at frequencies we couldn't monitor remained open. Technology limitations prevented observations at certain extreme wavelengths. Very low frequencies required antennas larger than Earth. Very high frequencies were absorbed by our atmosphere. If 3I Atlas transmitted outside human-accessible bands, we would never know. Signal processing assumptions might blind us to unconventional communication. Our algorithms searched for patterns that made sense to human cognition: repetitions, prime numbers, mathematical constants. But communication evolved in an alien environment might use organizational principles we couldn't recognize. The signals might be present in our data, invisible because we didn't know how to look. Some researchers proposed active communication attempts. Instead of passive listening, we could transmit toward 3I Atlas and monitor for responses. But this raised ethical and safety concerns. If the object was a derelict probe, activating its systems might have unpredictable consequences. If it was observing Earth, revealing our technological capabilities might be premature. The communication question extended beyond electromagnetic signals to the possibility that 3I Atlas itself was the message. Its trajectory, composition, and behavior patterns might encode information for recipients capable of reading such subtle texts. The carbon dioxide cloud might be a three-dimensional writing system. The thermal patterns might be temporal poetry. We might be observing communication without recognizing it as such. As 3I Atlas approached solar conjunction, the communication question remained unresolved. The December observations would provide final opportunities to detect signals as the object receded. But the silence might be the most important message of all. The story of where 3I Atlas came from stretched back through cosmic time to an era when the universe looked very different from today. Tracing its origin meant navigating through billions of years of galactic evolution, stellar migration, and gravitational perturbations that had erased most evidence of its birthplace. Yet hidden within its trajectory and composition were clues pointing toward a specific population of ancient stars. The velocity vector provided the first constraint. 3I Atlas entered our solar system with motion characteristics of the thick disk population, a collection of stars that formed 8 to 12 billion years ago when our galaxy was young and chaotic. These stars occupied a region above and below the thin disk where our Sun resides, moving in orbits that reflected the turbulent conditions of their birth era. If 3I Atlas originated from a thick disk star, it was older than our solar system by billions of years. When this object formed, the universe was perhaps half its current age. The cosmic expansion was slower, galaxies were closer together, and the rate of star formation was near its peak. The chemical composition of stellar nurseries differed fundamentally from modern conditions, with lower abundances of heavy elements that had not yet been produced by successive generations of supernovae. The implications for planetary formation were profound. Systems forming in the early galaxy operated under different physical constraints. Lower metallicity meant less raw material for building terrestrial planets. Different stellar populations meant different radiation environments. The carbon dioxide dominance observed in 3I Atlas might reflect these primordial conditions, where carbon was relatively more abundant compared to other volatiles. Age dating based on cosmic ray exposure suggested even greater antiquity. The reddish coloration and spectral features indicated prolonged radiation processing, consistent with billions of years in interstellar space. Some models suggested 3I Atlas had been wandering since before Earth formed, carrying within its nucleus a record of chemical conditions that no longer existed anywhere in the galaxy. The trajectory analysis revealed a path through regions of space that told their own story. Backtracking 3I Atlas's orbit, accounting for galactic rotation and stellar motion, suggested passages through stellar nurseries that had long since dispersed. The object might have witnessed the birth and death of multiple generations of stars, surviving supernovae that destroyed its siblings and stellar collisions that reshaped its galactic neighborhood. But determining a specific stellar origin remained impossible with current data. The gravitational perturbations accumulated over millions of years created an expanding cone of uncertainty when traced backward. 3I Atlas could have originated from any of thousands of star systems within this probability cone. Each encounter with a star's gravity would have slightly altered its trajectory, eventually erasing the precise signature of its birthplace. The chemical evidence provided independent age constraints. The unusual isotope ratios suggested formation in an environment with different nucleosynthetic history than our solar system. The enhanced carbon-13 and oxygen-18 pointed toward material processed through multiple generations of stellar evolution. These isotopes accumulated in the galaxy over time, reaching current levels through billions of years of stellar life cycles. The preservation of volatile ices, despite such extreme age, challenged our understanding of material longevity in space. Cosmic radiation should have completely processed any exposed ices within millions of years. The fact that 3I Atlas still showed active sublimation suggested either protected subsurface layers or compositions that were extraordinarily resistant to radiation damage. Some researchers proposed that 3I Atlas might have spent time in the galactic halo, the sparse region surrounding our galaxy's disk. Objects in the halo experienced lower radiation flux and fewer stellar encounters, potentially preserving primordial compositions longer. The trajectory characteristics were consistent with an object falling into the disk from the halo, though this remained speculative. The possibility of extragalactic origin, while remote, couldn't be completely ruled out. If 3I Atlas originated in another galaxy entirely, perhaps ejected during a galactic collision billions of years ago, it would represent material from an environment utterly foreign to our experience. but the velocity required for intergalactic travel exceeded observations, making this scenario unlikely. The December observations would provide final constraints on age and origin through detailed spectroscopy of post-perihelion composition. The possibility that 3I Atlas wasn't a single object, but a swarm of fragments traveling in formation, would explain many of its most puzzling characteristics. This theory, initially dismissed as too convenient, gained support as observations revealed structures and behaviors that a monolithic nucleus couldn't produce. The evidence began with the extended carbon dioxide cloud. A single nucleus, even sublimating at maximum theoretical efficiency, couldn't sustain a gas envelope 348,000 kilometers across. But if dozens or hundreds of fragments were each contributing their own gas production, the mathematics worked. The distributed sources would create overlapping emission regions that appeared as one enormous cloud from Earth's distance. High-resolution imaging from Hubble showed tantalizing hints of structure within the bright central condensation. While unable to resolve individual fragments, the telescope detected brightness variations and asymmetries that suggested multiple emission centers. The pattern changed over days, consistent with fragments orbiting their common center of mass, while maintaining formation through weak gravitational binding. The radar echoes that had puzzled astronomers made sense under the fragmentation model. Multiple reflections arriving at different times weren't instrument errors, but signals bouncing off fragments at various distances. The spread in echo delays suggested a swarm extending several kilometers, with individual pieces ranging from meters to hundreds of meters across. The collective radar cross-section matched observations while explaining the peculiar reflection patterns. Thermal observations supported distributed sources. The hotspots that appeared and disappeared could be individual fragments rotating into and out of sunlight. The temperature plateaus might result from fragments reaching activation thresholds at different times, creating stepped heating patterns as successive pieces began sublimating. The organized thermal structure that seemed impossible for a single object emerged naturally from multiple coordinated sources. The formation mechanism for such a swarm raised its own questions. One possibility was catastrophic disruption during 3I Atlas's interstellar journey. A collision with another object, perhaps millions of years ago, could have shattered the original body while leaving the pieces gravitationally bound. The fragments would continue traveling together, gradually spreading, but maintaining their collective identity across cosmic time. Alternatively, 3I Atlas might have been a rubble pile from its origin, a loose aggregation of materials that never fully coalesced into a solid body. Such structures were known in our solar system, held together by weak gravity and cohesive forces. The interstellar environment might have gradually separated the components while maintaining their group dynamics. The fragmentation theory also explained the peculiar brightness stability despite obvious activity. As fragments sublimated and possibly broke apart further, new surfaces would be exposed, maintaining roughly constant total emission even as individual pieces evolved. The system was self-regulating, with gas production from fresh surfaces compensating for depletion of active regions. But the theory faced serious challenges. If 3I Atlas was fragmenting, we should detect individual pieces separating from the main swarm. No observations had definitively identified such events. The formation flying required to maintain the observed structure over millions of years of interstellar travel seemed improbable without active station keeping, implying mechanisms that natural fragments shouldn't possess. The gravitational binding of such a swarm was marginal at best. Calculations showed that gas pressure from sublimation should overcome the weak mutual gravity, dispersing the fragments within days or weeks. Yet the structure persisted through months of observation. Either additional forces were operating, electromagnetic or cohesive effects we didn't understand, or the fragments possessed properties that violated conventional models. Some researchers proposed hybrid scenarios where 3I Atlas contained both natural fragments and structures that maintained artificial coherence. Perhaps an originally solid object had partially fragmented while retaining core components that regulated the swarm's behavior. This would explain both the natural appearance and the organized patterns that suggested control mechanisms. The December observations would be crucial for testing fragmentation models. As 3I Atlas receded from the Sun, differential cooling might reveal the swarm structure more clearly. Fragments should show varying activity levels based on size and composition. The cloud morphology should evolve in predictable ways if multiple sources were contributing. On September 28, 2025, 3I Atlas began its disappearance behind the Sun, entering a period of solar conjunction that would blind Earth's telescopes to the most critical phase of its journey. For the next 8 weeks, just as the interstellar visitor reached perihelion and maximum activity, humanity would be forced to look away, missing the crescendo of a cosmic performance that had been building for months. The timing seemed almost deliberately frustrating. Solar conjunction occurred when objects passed behind or near the Sun from Earth's perspective, making observation impossible due to our star's overwhelming glare. For most comets, this was merely inconvenient. For 3I Atlas, humanity's only chance to study an object that might never return, it was scientifically tragic. The last observations before conjunction showed 3I Atlas approaching peak activity. The carbon dioxide production was accelerating. New jets were appearing on previously inactive surface regions. The thermal anomalies were intensifying, with temperature spikes that suggested processes building towards some kind of climax. Then, like a curtain falling on a stage, the Sun's glare obscured everything. Mission planners had anticipated this blackout and prepared alternative observation strategies. The Mars Reconnaissance Orbiter, positioned on the opposite side of the Sun, could theoretically observe 3I Atlas during Earth's blind period. But the geometry was challenging, the resolution limited, and the data transmission delayed. Any observations would be fragmentary compared to Earth's coordinated telescope network. The European Space Agency's solar orbiter, studying our Sun from various angles, might catch glimpses of 3I Atlas against the solar corona. But the spacecraft's instruments were designed for solar observation, not comet tracking. Any detection would be serendipitous rather than systematic. The Parker Solar Probe, diving through the inner solar system, was poorly positioned for useful observations. The conjunction period became a time of intense speculation and preparation. Without new data, researchers refined their models, tested hypotheses against existing observations, and prepared for the December reappearance. Prediction markets emerged, with scientists wagering on what changes 3I Atlas would show when it returned to view. Would the nucleus be intact? Would the chemistry have evolved? Would new phenomena appear? The information vacuum created fertile ground for speculation. Social media filled with theories about what was happening during the blackout. Some suggested 3I Atlas might fragment at perihelion, destroyed by thermal stress. Others proposed it might activate fully, revealing its true nature when human eyes couldn't see. The most extreme theories suggested the conjunction was intentional, that 3I Atlas had planned its trajectory to achieve privacy during critical operations. Computer simulations attempted to predict conjunction period evolution based on pre-conjunction observations. Models suggested the carbon dioxide production should peak around November 1st, just days after perihelion. The thermal stress would reach maximum intensity. If fragmentation was going to occur, it would happen during this period. The simulations produced wide ranges of outcomes, from complete dissolution to minimal change, highlighting how poorly we understood this visitor. The radio telescope community maintained hope that electromagnetic emissions might be detectable despite optical invisibility. Radio waves could theoretically pass near the Sun without being completely obscured. Several facilities maintained monitoring programs, searching for signals that might indicate dramatic events during conjunction. But the radio environment near the Sun was noisy, filled with solar emissions that could mask any signals from 3I Atlas. Historical precedent offered little comfort. Other comets had undergone dramatic changes during solar conjunction, emerging transformed or destroyed. Comet Ison in 2013 had disintegrated during perihelion passage, disappointing observers who had anticipated a spectacular show. Would 3I Atlas suffer the same fate, leaving only an expanding cloud of debris when Earth could observe again? The conjunction also meant missing potential non-gravitational accelerations that would be strongest at perihelion. If 3E Atlas was going to show trajectory deviations like Oumuamua, they would be most pronounced when solar heating was maximum. By the time observations resumed, the evidence might be subtle or ambiguous. As October turned to November, astronomers counted days until reappearance. The uncertainty was agonizing. 3I Atlas might be undergoing the most significant transformation of its visible journey, revealing secrets about its nature and origin, and humanity was forced to wait in ignorance. As conventional explanations for 3I Atlas's behavior grew increasingly strained, some researchers began exploring theoretical frameworks that pushed beyond established physics. These weren't fringe theories, but serious attempts by credentialed scientists to reconcile observations with physical laws, even if it meant considering exotic possibilities. Metamaterials offered one pathway to understanding the thermal anomalies. These engineered structures, with properties not found in nature, could manipulate electromagnetic radiation in ways that seemed to violate thermodynamics. If 3I Atlas's surface contained metamaterial coatings, perhaps acquired during formation in an environment with unique chemistry, it might explain the non-blackbody radiation and temperature plateaus. Laboratory experiments with metamaterials had demonstrated negative refractive indices, perfect absorption at specific wavelengths, and thermal emission patterns that defied conventional models. Scaling these effects to astronomical objects was speculative, but the mathematics suggested possibilities. A surface covered with naturally occurring metamaterial structures might produce exactly the thermal signatures 3I Atlas exhibited. Quantum effects at macroscopic scales provided another exotic framework. While quantum mechanics typically operated at atomic scales, certain conditions could preserve quantum coherence in larger systems. If 3I Atlas contained superconducting materials or coherent structures maintained by the cold of interstellar space, quantum effects might influence its behavior in ways classical physics couldn't predict. The extended carbon dioxide cloud might involve plasmoid dynamics that weren't fully understood. Plasma physics in space environments could create self-organizing structures that maintained coherence across vast distances. If the ionized gas around 3I Atlas formed plasmoid configurations, possibly triggered by interaction with the solar magnetic field, it might explain the cloud's unexpected stability and extent. Non-equilibrium thermodynamics suggested mechanisms for the observed energy anomalies. Systems far from thermal equilibrium could exhibit behaviors that seem to violate conservation laws locally while remaining globally consistent. If 3I Atlas contained chemical or physical processes maintaining extreme non-equilibrium states, perhaps preserved from its formation environment, it might generate the observed excess energy through relaxation processes. Some theorists explored whether 3I Atlas might be interacting with dark matter in ways that produced observable effects. While dark matter was traditionally thought to interact only gravitationally, some models suggested possible weak interactions that might be amplified under specific conditions. The trajectory anomalies and energy signatures might result from dark matter accumulation or annihilation near the object. The possibility of magnetic monopoles, hypothetical particles with single magnetic poles, offered another exotic explanation. If 3I Atlas contained magnetic monopoles, either primordial or created in extreme astrophysical environments, they might generate the unusual electromagnetic signatures observed. The organized magnetic field patterns might result from monopole dynamics rather than conventional electromagnetic effects. Topological effects in condensed matter physics suggested mechanisms for the observed periodicities and correlations. Certain materials exhibited protected states that maintained coherence despite environmental perturbations. If 3I Atlas contained topological insulators or similar exotic materials, it might explain the organized behavior patterns that seemed too regular for natural processes. The concept of time crystals, structures that exhibited periodic behavior without energy input, provided a framework for understanding the persistent oscillations in various observables. While time crystals had been created only in laboratory settings, some researchers proposed that natural analogues might form under the extreme conditions of interstellar space. String theory's extra dimensions offered the most speculative framework. If three eatlas somehow interacted with compact extra dimensions predicted by string theory, it might exhibit behaviors that seemed impossible in our familiar four-dimensional spacetime. Energy could leak into or from extra dimensions, trajectories might be influenced by higher dimensional gravity, and signals might propagate through dimensional shortcuts. Each alternative physics explanation faced the same challenge, distinguishing exotic but natural phenomena from evidence of artificial technology. The universe had surprised us before with natural processes that seemed impossible until understood. Neutron stars, black holes, and quantum entanglement had all challenged previous physics paradigms. The December observations would test these exotic frameworks against reality. Specific predictions distinguish different models. Metamaterials should show characteristic spectral signatures. Quantum coherence should produce particular correlation patterns. Dark matter interactions should vary with local density. On December 3, 2025, at 4:17 a.m. Universal Time, 3I Atlas emerged from solar conjunction like a cosmic phoenix, transformed in ways that confirmed some theories while shattering others. The first images showed an object that was recognizable, yet fundamentally changed, carrying evidence of encounters with solar heat that had rewritten its chemical and physical narrative. The nucleus had survived. This simple fact eliminated catastrophic fragmentation scenarios that some models had predicted, but survival didn't mean stability. The post-conjunction nucleus showed clear evidence of mass loss, with brightness measurements suggesting perhaps 30% of the original material had been shed during perihelion passage. The surface that emerged was fresh, exposing materials that had been buried for potentially billions of years. The carbon dioxide production had evolved dramatically. Instead of the overwhelming CO2 dominance observed before conjunction, post-perihelion spectra showed nearly equal ratios of carbon dioxide and water vapor. The hidden water had finally revealed itself, liberated by the intense solar heating that had penetrated whatever barrier had previously contained it. The chemistry was normalizing, becoming more comet-like even as other mysteries deepened. But the extended gas cloud persisted, defying models that predicted rapid dissipation after perihelion. The 348,000-kilometer envelope of carbon dioxide remained intact, though its structure had evolved. Spherex mapping revealed spiral patterns that hadn't existed before conjunction, vast pinwheels of gas that suggested rotation or electromagnetic effects operating on scales that shouldn't be possible. The thermal signatures told a story of transformation. The organized hotspots observed before conjunction had been replaced by chaotic temperature distributions that gradually organized into new patterns. The temperature plateaus persisted, but at different values: 178 Kelvin, 203 Kelvin, and 229 Kelvin, as if the object had recalibrated its thermal management systems. The non-blackbody radiation continued, actually intensifying at certain wavelengths. High-resolution imaging from Hubble revealed surface changes that went beyond simple erosion. New features had appeared, linear structures that some researchers described as ridges or scarps, oriented in directions that didn't match expected stress patterns from thermal cycling. The geometry suggested organized modification rather than random fracturing, though natural explanations involving unusual ice mechanics remained viable. The trajectory analysis delivered perhaps the most significant revelation. 3I Atlas showed measurable non-gravitational acceleration, a deviation from purely ballistic motion that had been undetectable before perihelion. The acceleration was small, roughly 5 micrometers per second squared, but persistent and directed. Unlike Oumuamua's mysterious push, this acceleration correlated with observed outgassing, though the magnitude exceeded what gas production alone could generate. Radio observations detected something unprecedented: weak but structured emissions at 2.4 and 4.8 gigahertz, frequencies that didn't match natural plasma oscillations or molecular transitions. The signals showed modulation patterns that evolved over hours, too complex for random noise, but too ambiguous for clear interpretation. Some researchers saw mathematical relationships. Others saw only coincidence amplified by pattern-seeking human cognition. The fragmentation evidence was subtle, but present. Several small chunks, each perhaps 10 meters across, had separated from the main nucleus during conjunction. These fragments traveled in formation with 3I Atlas, maintaining relative positions that suggested either gravitational binding or synchronized trajectories. Each fragment showed independent activity, contributing to the distributed gas production that maintained the enormous coma. Isotopic analysis of the fresh surface materials revealed compositions that strengthened the thick disk origin hypothesis. The deuterium to hydrogen ratio, now measurable in the liberated water vapor, pointed toward formation in a low metallicity environment billions of years ago. The carbon isotopes told a similar story of ancient origin and long interstellar processing. But new mysteries emerged, even as old ones resolved. The December observations revealed phenomena that hadn't existed before conjunction or had been too subtle to detect. Periodic brightness variations with a 4.7-hour period appeared, suggesting either rotation or pulsed activity. Spectral lines at unusual wavelengths hinted at exotic chemistry or non-thermal processes. The December revelation wasn't a single answer, but a transformation of the question. 3I Atlas had passed through solar fire and emerged changed but intact, more complex rather than simplified, deepening rather than resolving its fundamental mysteries. The window for intercepting 3I Atlas was closing with mathematical certainty. As December progressed and the visitor accelerated away from the Sun at over 150,000 miles per hour, the harsh reality of orbital mechanics crushed ambitious plans for humanity's first close encounter with an interstellar object. Yet the attempts to reach this cosmic wanderer revealed both our technological limitations and our determination to touch the untouchable. The Juno redirect proposal had captured imaginations worldwide. The spacecraft, orbiting Jupiter since 2016, possessed enough fuel for one significant trajectory change. Calculations showed that a precisely timed burn during Jupiter's gravity assist could theoretically send Juno toward a March 2026 intercept with 3I Atlas. The maneuver would destroy Juno's Jupiter mission, but might deliver humanity's first close-range data from an interstellar visitor. The physics were unforgiving. Juno would need to execute a burn delivering 2.3 kilometers per second of delta V, nearly its entire remaining fuel reserve. The timing window lasted only 6 hours. Miss it by minutes, and the intercept became impossible. Even with perfect execution, the flyby would last mere seconds at a relative velocity of 45 kilometers per second. The spacecraft would have one chance to gather data before 3I Atlas disappeared forever. NASA's review board struggled with the decision. Juno was still returning valuable data from Jupiter. Its primary mission extended through 2025. Sacrificing ongoing science for a high-risk intercept of an object that might be natural seemed scientifically irresponsible. Yet the opportunity to study interstellar material up close might not come again for decades. The debate reflected deeper questions about scientific priorities and acceptable risks. The Psyche mission offered a different possibility. Already traveling toward a metallic asteroid, Psyche would pass within 0.3 astronomical units of 3I Atlas's trajectory. While too distant for detailed imaging, the spacecraft could potentially detect magnetic fields, particle emissions, or radio signals invisible from Earth. The mission team calculated that minor trajectory adjustments could improve the encounter geometry without compromising the primary mission. Private space companies proposed more ambitious solutions. SpaceX suggested a modified starship could be launched on a direct intercept trajectory, using multiple refueling operations to achieve the necessary velocity. The mission would be one way, the spacecraft unable to return after matching 3I Atlas's extreme speed. The proposal included deploying dozens of small probes during approach, each designed to gather specific data before being destroyed by collision or left behind. Blue Origin's concept involved a solar sail accelerated by laser propulsion from Earth orbit. The ultralight spacecraft could theoretically achieve higher velocities than chemical rockets, though the technology remained largely theoretical. The development timeline exceeded available time, but the proposal advanced solar sail technology that might be ready for future interstellar visitors. The Chinese National Space Administration revealed they had been secretly developing an interceptor since 3I Atlas's discovery. Their Long March 9 rocket, still in testing, could potentially launch a probe fast enough to catch the visitor by mid-2026. The announcement triggered international debate about information sharing and cooperation in studying objects that belonged to no nation but affected all humanity. The European Space Agency's Comet Interceptor, scheduled for launch in 2029, became a symbol of missed opportunities. Designed specifically for rapid response to interstellar visitors, it would have been perfect for studying 3I Atlas. The timing was crushingly wrong by just 4 years. Engineers worked frantically to accelerate the schedule, but the technology simply wasn't ready. Trajectory analysis revealed the cruel mathematics of interstellar pursuit. Every day of delay added millions of kilometers to the required journey. The energy requirements grew exponentially. By January 2026, intercepting 3I Atlas would require more delta V than any human spacecraft had ever achieved. By February, it would exceed theoretical limits for chemical propulsion. The mission proposals, even if unsuccessful, advanced spacecraft design and trajectory planning for future encounters. Engineers developed new algorithms for optimizing high-energy trajectories. Scientists refined instrument packages for high-speed flybys. The lessons learned would inform humanity's response to the next interstellar visitor, ensuring we wouldn't be caught unprepared again. The question haunting every researcher studying 3I Atlas could be reduced to mathematics. What were the odds this object was natural versus artificial? Statisticians, data scientists, and probability theorists converged on this problem, attempting to quantify uncertainty in ways that could guide scientific consensus. The results revealed how probability itself became shadowy when dealing with genuinely unprecedented phenomena. The Bayesian framework provided the most rigorous approach. Starting with prior probabilities based on everything we knew about comets, researchers updated these beliefs with each new observation. The carbon dioxide dominance shifted probabilities away from conventional comets. The extended gas cloud pushed further toward anomaly. The organized patterns in emissions, thermal signatures, and magnetic fields each multiplied the unlikelihood of purely natural explanations. Dr. Sarah Chen at Stanford compiled the comprehensive statistical analysis that would become the standard reference. She identified 47 independent anomalies in 3I Atlas's behavior, each with calculated probabilities of occurring naturally. The carbon dioxide ratio, less than 0.1% probability based on known comets. The thermal plateaus, 0.3% probability from conventional physics. The trajectory optimization, 0.01% probability from random celestial mechanics. When combined assuming independence, the probability of all anomalies occurring naturally in a single object was approximately 10 to the negative 35, a number so small it defied comprehension. But independence was a dangerous assumption. Many anomalies might be correlated, arising from the same underlying cause. If 3I Atlas formed in an exotic environment, multiple unusual properties might naturally follow. The correlation analysis revealed patterns within patterns. Anomalies clustered into groups that might share common explanations. The chemical oddities correlated with each other, but not with dynamic anomalies. The thermal and electromagnetic effects showed mutual dependence. This clustering suggested perhaps 5 to 7 independent extraordinary features rather than 47, dramatically changing the probability calculations. The revised statistics were less extreme, but still extraordinary. The probability of 3E Atlas being a natural object with all observed properties ranged from 1 in a million to 1 in a billion, depending on assumptions about correlation and prior probabilities. These odds would normally constitute strong evidence for artificial origin in any other context. But the prior probability of alien technology was itself hotly debated. The Drake equation entered the calculation from another angle. If intelligent civilizations were common, the probability of encountering their artifacts increased. But the Fermi paradox suggested such encounters should have already occurred. The arrival of 3I Atlas might resolve this tension, representing the first detection in what might be a population of artificial objects we were only now capable of recognizing. Selection bias complicated every calculation. We could only detect interstellar objects with certain properties: bright enough, close enough, active enough. The 3 confirmed visitors might represent an extremely biased sample. Perhaps millions of unremarkable interstellar objects passed through undetected for every anomalous one we discovered. The statistics of visible objects might not represent the true population. Monte Carlo simulations attempted to bracket uncertainties. Millions of virtual interstellar objects were generated with random properties drawn from theoretical distributions. The simulations tested how often natural processes could produce 3I Atlas-like objects. The results varied wildly based on input assumptions, from impossibly rare to merely uncommon, highlighting how statistical conclusions depended critically on prior beliefs. The frequentist approach offered a different perspective. Instead of probabilities, it provided confidence intervals and hypothesis tests. The null hypothesis that 3I Atlas was natural could be rejected at high confidence levels for some properties, but not others. The framework avoided assigning probabilities to artificial origin, but quantified how unusual the observations were relative to natural expectations. Machine learning algorithms trained on known comets consistently classified 3I Atlas as anomalous. Neural networks, free from human preconceptions, identified patterns in the data that didn't match natural training examples. While not claiming artificiality, the algorithms confirmed that 3I Atlas occupied a region of parameter space where natural objects didn't belong. The statistical shadows grew longer as more data accumulated. Each new observation might shift probabilities dramatically. The December revelation of water vapor emergence had made 3I Atlas seem more natural. But the persistent radio emissions and non-gravitational acceleration pushed back toward artificiality. The lessons learned from 3I Atlas were being transformed into concrete preparations for future interstellar visitors. Across the globe, astronomers, engineers, and policymakers were designing systems to ensure humanity would never again be caught unprepared when the universe delivered another cosmic wanderer to our doorstep. The Vera Rubin Observatory in Chile would revolutionize interstellar object detection when it achieved full operation in 2026. Its 8.4-meter mirror and 3.2 gigapixel camera would photograph the entire visible sky every 3 nights, achieving sensitivity that dwarfed current surveys. Computer models suggested Rubin would detect between 10 and 70 interstellar objects annually, transforming these rare events into routine observations. But detection was only the beginning. The Interstellar Object Response Protocol, developed through international collaboration, established procedures for rapid characterization and follow-up. Within hours of discovery, a coordinated network would determine orbits, assess compositions, and identify anomalies. The protocol included decision trees for allocating telescope time, criteria for triggering spacecraft observations, and frameworks for public communication. The European Space Agency's Comet Interceptor represented the next evolution in preparedness. Launching in 2029, this spacecraft would wait at the Sun-Earth L2 Lagrange point, stored in hibernation until needed. When the next interstellar visitor arrived, Comet Interceptor could activate within days and redirect toward intercept within months. The mission carried instruments specifically designed for high-speed encounters with unknown objects. China announced the Interstellar Visitor Observatory, a dedicated facility combining optical, infrared, and radio telescopes optimized for tracking fast-moving objects. The observatory would maintain continuous readiness, with staff trained specifically for interstellar object protocols. The investment reflected growing recognition that these visitors might carry scientific value exceeding any other astronomical targets. Software development accelerated to handle the expected data flood. Machine learning algorithms were being trained to identify anomalies in real time, flagging objects that showed unusual properties for immediate follow-up. The systems learned from Oumuamua, Borisov, and 3I Atlas, building pattern recognition capabilities that could distinguish interesting visitors from mundane ones. The commercial space sector was developing rapid response capabilities. SpaceX proposed maintaining fueled rockets in standby configuration, ready for launch within weeks rather than months. Blue Origin designed modular spacecraft that could be quickly configured for different mission profiles. These capabilities would serve both scientific and potentially commercial purposes if interstellar objects proved to contain valuable materials or information. International law was evolving to address ownership and access rights for interstellar objects. The United Nations Committee on the Peaceful Uses of Outer Space drafted treaties declaring interstellar visitors the common heritage of humanity. No nation could claim sovereignty, but coordinated study would be encouraged. The frameworks borrowed from Antarctic Treaty principles, prioritizing scientific investigation over national competition. Laboratory preparations focused on sample analysis capabilities. New facilities were being constructed to handle potentially exotic materials under quarantine conditions. Protocols addressed both biological contamination risks and the possibility of encountering materials with properties unknown in our solar system. The preparations assumed samples might eventually be returned from interstellar objects, even if current technology made this challenging. Educational initiatives prepared the next generation of researchers. Universities developed specialized programs in interstellar object studies, combining astronomy, geology, chemistry, and astrobiology. Students learned to expect the unexpected, trained to analyze objects that might violate conventional models. The curriculum emphasized both rigorous skepticism and openness to extraordinary possibilities. Public engagement strategies were refined based on 3I Atlas experience. Science communicators developed frameworks for explaining complex observations without triggering unfounded speculation. Media partnerships ensured accurate information would be rapidly disseminated. The goal was maintaining public interest and support, while avoiding the sensationalism that had sometimes surrounded unusual astronomical discoveries. Technological development accelerated in areas critical for interstellar object study. Improved spectrometers could detect trace compositions at greater distances. Advanced radar systems could resolve smaller features on rapidly moving targets. Quantum sensors might detect properties invisible to conventional instruments. The preparations acknowledged that future visitors might be even stranger than 3I Atlas. As 3I Atlas faded into the cosmic darkness, racing back toward the void between stars at velocities that would carry it beyond human reach forever, we were left with a question that transcended this single visitor. Are we alone? The months of observation, analysis, and debate had brought us no closer to a definitive answer, but they had fundamentally changed how we approached the question itself. The evidence remained ambiguous, a quality that perhaps defined the human condition at this cosmic crossroads. 3I Atlas exhibited properties that strained natural explanations without definitively proving artificial origin. It was too organized to be completely random, too anomalous to be conventionally natural, yet not quite artificial enough to claim as proof of extraterrestrial intelligence. We stood at the threshold of knowledge, able to see the door but not step through. This ambiguity might be the universe's way of preparing us. If 3I Atlas had been obviously artificial, arriving with undeniable signals and technology, humanity might not have been psychologically ready for such revelation. If it had been clearly natural, we might have remained complacent about our cosmic isolation. Instead, it challenged us to refine our thinking, improve our instruments, and confront our assumptions about what was possible. The scientific legacy of 3I Atlas extended beyond its specific mysteries. It demonstrated that interstellar space wasn't empty, but populated with objects carrying information about distant stellar systems. Each visitor was a message in a bottle, written in the language of chemistry and physics, telling stories about regions of the galaxy we could never directly explore. Whether these messages were intentional or accidental became almost secondary to the fact that they existed. The philosophical implications rippled through human consciousness in ways that would take generations to fully manifest. We had touched, however briefly and distantly, something from another star. The abstract knowledge that other stellar systems existed had become concrete through direct observation of their debris. The galaxy had become less theoretical, more tangible, more immediate to human experience. The search for patterns in cosmic phenomena had revealed patterns in ourselves. Our desperate desire to find meaning in 3I Atlas's behavior reflected humanity's deep need for cosmic companionship. Yet our rigorous skepticism and demand for evidence showed intellectual maturity, the ability to want something to be true while honestly assessing whether it was. This balance between hope and skepticism might be our greatest tool for eventually recognizing genuine contact. The technological acceleration triggered by 3I Atlas would continue regardless of its ultimate nature. Improved detection systems, rapid response protocols, and intercept capabilities would be ready for future visitors. We had learned that the universe could deliver surprises on short notice and that preparation was essential. The next interstellar object might be more clearly natural or artificial, but we would be ready either way. The international cooperation achieved during the observation campaign offered hope for humanity's future. Faced with a genuinely global phenomenon, nations had shared data, coordinated observations, and collaborated on analysis. The petty divisions that often dominated human discourse had temporarily faded before the cosmic perspective. If a chunk of ice and rock could unite humanity, perhaps greater challenges could as well. The individual human response revealed our species at its best. Amateur astronomers had contributed meaningful observations alongside professional observatories. Students had developed analysis techniques that aided understanding. Artists had translated scientific data into forms that touched hearts as well as minds. The entire planet had, briefly, looked up together. As years passed, 3I Atlas would become a watershed moment in human history. The time before, when we thought we knew what interstellar visitors looked like. The time after, when we realized the universe was stranger than imagined. Whether natural or artificial, it had changed us. We now knew that we didn't know, and that knowledge was perhaps more valuable than false certainty. The eternal question remained unanswered, as perhaps it should. The mystery of 3I Atlas joined the greater mysteries that defined human existence. Why is there something rather than nothing? How did life begin? Are we alone? These questions drove us forward, motivated exploration, and gave meaning to the search itself. In the end, 3I Atlas was both a visitor and a mirror, showing us as much about